In the last example, I did not show the second distributivity identity explicitly because one, you can do it in a very similar way. There is no need to repeat all that. And number two, in a Boolean algebra, meet and join operations are duals. What does that mean to be duals? Suppose that you have an identity like x join with 0 is equal to x. The dual of this expression you can obtain by switching meets with joins and tops with bottoms. So what you do is you switch this one into a meet and this bottom into a top. The variables are the same, and this is the dual of this original expression. And if you apply the same thing to this, you will obtain this original one. So they are duals of each other. And when you have an identity that is true, if you take its dual, that will also always be true. And this is not a coincidence, because if you take the inverse of any poset on a set, the inverse will also be a poset, because that will also be reflexive, anti-symmetric, symmetric, and transitive. You just change the order of the arrows, and top becomes bottom, bottom becomes top, and meet and join switch functionalities. So the duals will always have the same truth value. Okay, so in general, when you are dealing with an identity in a Boolean algebra, you don't need to prove its dual. When you show one identity is true, its dual is automatically true. Okay, and for any finite set, the structure, the power set of a finite set A, along with the binary operators, union and intersection, and for the complement, you have the set complement, and the bottom element is empty set, and the top element is this set A. This is a Boolean algebra. Any finite set, this is a Boolean algebra. This is in fact the set algebra. Okay, with respect to addition becomes union, multiplication becomes intersection, complements becomes set complement, and the bottom element, the least element, is the empty set, and the greatest element is set A itself. And in fact, all finite Boolean algebras must have a cardinality that's a power of 2, and they are all isomorphic to a set algebra. Okay, so a set algebra is in this form. Let's say your set is a singleton. In this case, you just have the two-element Boolean algebra. This is exactly isomorphic to the propositional logic setting. This is 0, 1, or this is false, true. And all the operations with meet and join boils down to ands, ors. You can see this as, do you include in your set, do you include the element A? No. Do you include element A? Yes. You can see this in this way. Or increase the cardinality. Let's say your underlying set is AB. Now you have a 4-element Boolean algebra. The bottom, the top is AB, the bottom is the empty set, and you have the singletons here, incomparable with each other, but this is the lattice. I'm not showing all transitive branches. Okay, so you see you have a 4-element Boolean algebra here. The meet of the singletons, for instance, is empty set. The join of the singletons is set A, B, etc. If you have 3 elements, A, B, C, then this would be more complicated. You would have at the bottom the empty set. Here you would have the singletons. And here you have 2-element sets, AC and BC. And at the top you would have ABC. Okay, so this here, this, and this here, this, A, B, and C. B goes to this one and this one. C goes to this one and this one. And these all go to this. Okay. If you remember the previous example, the divisors of 30, you have a very similar structure. You have 1 at the bottom, you have 30 here, and you have 2, 3, and 5 here. And then you have 6 here related to these, and you have 10 related to these two, and you have 15 related to these two, and all related to the 30, and 1 is related to all these. Same structure. And why is that? Because they are isomorphic, and that's the exact same structure. In this lattice, or in this Boolean algebra, 1 corresponds to 2 to the power 0, 3 to the power 0, 5 to the power 0. So 0, 0, 0. All possible elements excluded. 2 corresponds to 2 to 1, 3 to 0, 5 to 0. This corresponds to 2 to 0, 3 to 1, 5 to 0, etc. And similarly, this one, for instance, you have do not include A, include B, exclude C. This one, exclude A, exclude B, include C. Or this one, include A, exclude B, include C. So this one is like, I don't know, 0, 0, 1. This is like 0, 1, 0. This is like 1, 0, 0. And this one is like 0, 1, 1. This one 101, this one 110, and this one 111. It's the same structure, okay? And if you would like to pull up the poset, for instance, for the divisors of not 30 but let's say 60, it will not be a Boolean algebra because 2 will be repeated, and you cannot represent it like a set because it will be 60 is equal to 2 to the power 2 times 3 to the power 1, 5 to the power 1. Since 2 is repeated, it's going to be a poset, yes, but it's not going to be a Boolean algebra. Okay, so every set algebra is the common structure you see as a Boolean algebra. And finally, for this week, we define what we call an algebra. This is one of the most general settings, a vector space on set V coupled with a field F of scalars equipped with an additionally binary operation, which is we denote as scalar multiplication, or rather is vector multiplication in this case, from the Cartesian product of V by itself to V, such that this product is distributive over addition in the vector field, in the vector space, and it is compatible with scalar multiplication in this way, okay? C1, V1, C here is a scalar, V is a vector, times C2, V2. Now, there is a multiplication here, but it's a scalar multiplication. You also have a scalar multiplication here. This here is a vector multiplication, and the right-hand side, I have, this is not a scalar multiplication, but it's the ordinary multiplication in the field of scalars. This here is matrix multiplication, vector multiplication, and this multiplication here is scaling. So if this is satisfied, this structure is called an algebra over a field. Algebra here doesn't refer to the subject, it refers to this structure specifically. So you have, as an algebraic structure, we call this an algebra over a field, or simply an algebra.